Welcome back, everybody. Oh, microphone. We're not quite ready to roll yet. One moment. I was feeling all proud of myself because I remembered to share my screen, and then I forgot this. All right. Got some more cold people walking in. There we go.
It smells so good.
Yes. All right. There we go. Now we're ready to roll. Got everything rolling. So welcome back. I sent out a note letting you know about a schedule change. Am I hearing a dinging? Am I losing my mind? Oh, that's not me. Okay. Don't know what's going on. In terms of the schedule, I have it set up initially to where you have something to do every other week is the idea in terms of homeworks every other week or the formative assessments every other week. But that's predicated on us getting through the material that I wanted to assess you on. And so if we get behind relative to what I had thought we would do, then I have to push these things back. So I've moved back homework 2 to be due March 2nd. That's a Monday. I figured I was going to have it due Friday, and I thought, well, I may as well give you the weekend because that doesn't matter to me. We'll be able to go over it when we come back on the 3rd. So homework 2 is out. You're able to start working on it now, but we haven't gotten through everything that it covers, and so I want to make sure that we have time to do that in class, make sure everyone's feeling good about that before you sit down to try and do it. And I'm juggling the stuff that's after it to try and keep things spaced as well. My hope is that we will be all the way through homework 3 by the time spring break hits, which is in 4 weeks. Hang in there. This is week 5 already, folks. So yes, week 9 is spring break. All right, so stuff we've been talking about. Apparently PowerPoint does not want to participate today, but that's fine. We're talking about how to ask questions about statistics, about summaries of information from our sample. And we've done 2 instances so far. One is being able to test the mean of a variable against the population mean. So that one, the example that we came up with in terms of when you might want to do that is if you are trying to demonstrate some sort of representativeness of your sample relative to what is supposed to be in the population. So to demonstrate that, you would need to know 3 things. You would need to know what it's supposed to be, population mean, what your sample's mean is, and what your sample's standard error of the mean is. If you know those 3 things, then you can answer the question as to whether or not your sample mean is off in a significant way from what it's supposed to be, or whether it's within expected variation. So the question is then, in terms of translating that decision, am I hoping for a significant result, meaning that I reject the null hypothesis of the population mean? Or am I hoping for a non-significant result, meaning I do not reject, I don't have enough evidence to say that it's unexpected? Significant result is usually the one that we want, but if you want to say that your sample is similar to the population that it's intended to represent,
We want it to be the same.
if we want it to be the same, do we want it to be significant, the result to be significant of the test? We don't. Actually, in that case, we are hoping that the variation that we have of our sample mean is within the expected territory relative to what it's supposed to be. So this whole language of reject versus do not reject, that whole thing, people don't talk like that. That's something that you get taught sort of to emphasize what you're actually trying to say, but then there's a shortcut to the language that shows up much more likely. And then it's either the result is significant or not significant. Significant means unexpected. It means that it is unlikely that that result would happen if the null hypothesis were true. Null hypothesis is the thing that you are expecting to find. So in the context of a sample versus a population mean, it's a comparison of those means. In the context of association, it's usually an expectation of a null hypothesis of 0. So we started looking at one measure of association. Remember this? These pictures? Scatter plots. This is our new friend Pearson's correlation. It's designed to measure the extent of linear relationship between two quantitative variables. R goes from -1 to +1. It's bounded. An R of 0 means there's no relationship whatsoever. An R of 1 means there's a perfect relationship that if you are higher than everyone else on X, you are likely to be higher than everyone else on Y. A -1 is also a perfect relationship, but it means the opposite. If you're higher on X, you are likely to be lower on Y. The things that go into that, each variable's mean, variance, and covariance. So covariance is a necessary step to getting to correlation, but it's somewhat problematic to interpret because it's in a metric that is specific to the two variables that you're looking at. So this is slide 23. We were looking at this before. If I have height and weight, and for a particular sample of 10 men, I have means, standard deviations, and variances here, as well as the range. If I put these numbers into the formulas on the previous page, I come up with something like 135 inch-pounds. And the correct answer to that is, what the hell is an inch-pound? Is 135 a lot? We don't know. You'd have to be able to interpret that in terms of the scale of the variables, and it's an arbitrary scaling. So to make that number interpretable, to make that number take on a scale that we immediately know what it means, we convert covariance to something called correlation. So we're standardizing covariance against the standard deviations of the variables from which it came. And then we have the correlation value that ranges from -1 to 1. The question is, then, how do we know if that correlation is significant? How do we know that it's noteworthy, that it falls into the unexpected territory, such that we would infer, yeah, we might actually have a relationship here? So this is our first example of doing something called null hypothesis significance testing, where we are comparing what we got in the sample against an expectation, a null hypothesis, of no relationship. So what else do we need to know to be able to do this? Well, we have to be able to map our result onto some kind of distribution that tells us about what is expected versus unexpected. And our best friend T is going to be the one that we use to do that. We have to decide how lenient we want to be in terms of where the breaking point is between expected and unexpected. So that refers to the amount of confidence that we have, confidence level or confidence interval. So if we want to say 95% confident, then only 5% of the time we would allow it to be deemed unexpected. That's our alpha level. So alpha is the opposite of confidence. If our test statistic, so the t-value that we compute to locate us on this distribution, exceeds some critical threshold based on where the confidence level is, then we reject the null. We say it's significant. It is unlikely that result would have happened by chance if the null hypothesis were true. Otherwise, if it falls within expected territory, we would do not reject, which is a mouthful. It just means that we don't have evidence to say that it's different than the null. We can't say the null is true because the null is actually never true. If you have enough people, you will always find something to be different than what you expect. It's just that we don't have enough evidence to say that with the current sample. So that's the idea of retaining or do not rejecting. So we have two things we need to know to be able to figure out where we are on the t-distribution for testing our correlation against 0. We need the correlation value. This is slide 27. And we need sample size. The more people you have, the easier it is to say that your correlation is unexpected. The fewer people you have, the stronger your correlation has to be before we are able to declare it unexpected or significantly different than 0. In my toy little example here, it worked out to be a correlation of 0.99, which generates a t-value of 25. So relative to this two-sided distribution, 25 is way out here on the right, way into unexpected territory. You would get a correlation of 0.99, like less than 0.0001% of the time, if the true correlation were 0. That's a really unexpected result. I did the same thing, this is slide 28, with two variables that I just made up to have no relationship. And it worked out that they actually did have a very small negative relationship. So what does a negative correlation of 0.13 tell us? Which way does the association go between x and y? Yeah, like the gestures, I'll take gestures. Yes, that's the negative slope. As x goes up, y goes down, or as y goes up, x goes down, whichever way you want to think about it, but they're in opposite directions. Now, is 0.13, negative 0.13, different than 0? Don't know yet. Got to plug it into the t formula that also takes into account the sample size. And that gives us a location on the t distribution right smack in the middle. So we would see a t value this extreme if the null hypothesis were true, if the correlation were actually 0, like 72% of the time. Well within expected territory. We do not have enough evidence to say it's not 0. Okay. How are we doing so far? Okay. So here is your first example of when nonlinear transformations would be used in statistics. Not for variables, but for results. The thing about Pearson's R is that it's bounded. The strongest value you can have is 1, either negative 1 or 1. So if I wanted to try to compute a standard error for my correlation, like what is the average offness of this sample correlation from the population one, in doing that, I have to make sure that the standard error doesn't result in correlations that are impossible. To solve that problem, there is something that you can ask software to do for you, which is called a Fisher Z transformation. I don't know why he picked Z, because Z is the same thing as the Z distribution and the Z score. This is a third instance of Z. Yes, you should be annoyed. There are 26 letters in the alphabet, and some of them show up more often than you would expect. Yes, but what this is the transformation itself. It is right here. It's 0.5 times the log of 1 plus the correlation over 1 minus the correlation. Gun to my head, I would not be able to recite that from memory. Okay, that's how infrequently I've actually seen this happen. But what that transformation does is shown on this graph here, where this is slide 29. Where the R sample correlation coefficient is on the bottom. The x-axis ranges from -1 to 1. That's the gray line. The yellow line is the result that happens when you translate that R into Fisher Z. It takes R's that are getting closer and closer to their boundary and it stretches them out. So Z goes on forever and ever. That way, you can compute a standard error in that Z metric, and it's based on sample size, as you would expect, because more people means more precision. You can then use that standard error to compute a confidence interval on the Z metric that's unbounded. But then when you back translate that Z metric down to R, the R's stay within their boundaries. So if you want to do this, this is something that is best done via software. That way you don't lose any information in terms of numeric precision, and I will be happy to show you how to do that. Okay. So linearity, what does Pearson's correlation tell you, and what doesn't it tell you? Turns out that Pearson's correlation measures an association between two quantitative variables of a particular very strict type. And that type is linear. The Pearson correlation is the slope of the line between the variables if they're both in a z-score metric where the mean is 0 and the variance is 1. So for instance, if I made a scatter plot of the height weight example that had a correlation of 0.99, here's the line through those points. And you can see there's very little offness here. You can almost perfectly predict someone's weight from their height or vice versa. The other variable pair that we looked at was sample correlation between random variables. Here's another one. This is what a correlation of 0.08 looks like. What would a line look like between two variables that are completely uncorrelated? R equals 0. And I'll take gestures on this one. Yeah, it'd be a ball. So if I had a line that best fit through that ball of points, what would the line look like? Flat. So as x goes up, who knows what happens to y? Could go up, could go down. We don't predict any change. So this line here is very close to flat. It's a very, very close to 0 correlation. So this is the type of relationship that is well captured by Pearson's correlation. Here are some relationships that are not well captured. U-shaped. So if I ran a Pearson's correlation between these two variables, there's a y variable here on the y-axis and another variable on the x-axis, that correlation works out to be 0.05. Does that line look like a good fit through those points? Just eyeball it. No. It looks like there is a negative relationship between y and x up to some point. So higher y values go with lower x values. And then after some point, higher y values go with higher x values. It should actually look more like a V. Pearson's correlation can't pick that up. That's not what it's designed to do. The good news is that I can teach you modeling approaches to catch those types of nonlinear relationships. In particular, this type of relationship would be characterized well by two different slopes, what's known as a linear spline. Here are some others. This is a famous result. The picture came from Wikipedia, but you see it in other intro textbooks. This is Anscombe's quartet. And in each of these pictures, there is a correlation of 0.82. The only picture that makes sense for is the top left. The top right is clearly missing a relationship that's bendy, some kind of nonlinear relationship where after a certain point, y doesn't go up anymore, even if x does. There is an almost perfect relationship down here on the bottom left that is ruined by one aberrant data point. That point we would say has high leverage. It has more influence on the result than each of the other points do. And x4 has the same problem, except that now the relationship is being driven by one aberrant point. Otherwise, there would be no relationship. X looks like it's a constant. So it's usually helpful to look at pictures like this to try and get a sense of whether a linear relationship even makes sense. I will be honest with you though, in real data, it's really hard to tell. And the more people you have, the more points there are, it's even harder to tell. So pictures are helpful descriptively up to a point, but at the end of the day, you'll always want to figure out some sort of empirical way to test whatever pattern you think you see and whether or not there is evidence that it's actually there. All right. Do you want to see how to make software give this to you?
Yes, please.
Yes, please. Yeah, I thought you might say that. So we're back in example 2, and this is one of the other techniques that you'll get a chance to practice in your homework too. So we did variable transformations, variable description, histograms, means. We tested the mean of education against 12. We tested the proportion of men and women against 50-50. And then we recoded gender to be able to get the other missing proportion, what's not given directly by the software. And now we are on page 7, halfway down. So proc-core, can you guess what core stands for? Correlation. Do you know what proc stands for? Procedure, yeah. Yeah, there's all kinds of procs. Unfortunately, the ones that would be most useful are not there, like proc taxes or proc discussion, things like that. I'd like to see that in SAS, if any SAS people are watching today. SAS code looks similar to the procs that you already know. The ones that you've gotten a chance to practice are proc freq, which gives frequencies, proc means, which gives means and standard deviations, and proc univariate, which gives more descriptive information univariately for one variable at a time. Each of those has a requirement that you specify which data set you'd like to ask the analysis to refer to. So for instance, this is work.example2. Things in blue here are SAS keywords that if you type this, it knows what you're asking for. Cov stands for covariance. That's something I'm doing for pedagogical reasons. It's not something you would typically look at in an analysis. Pearson stands for Pearson correlation. Fisher, this whole thing in here, Fisher Z. It's the how you get standard errors, how you get confidence intervals, and it also allows you the opportunity to test your correlation against any other null hypothesis that you want. So for instance, this is how I would test it against 0.5. This doesn't look right. I think I have an extra 0 in there somehow. It should just be rho. Do you remember what rho is? R-H-O? It's a Greek letter. It's a Greek letter. Yep. It looks sort of like P, but it's rho. That's how you specify the population correlation in the notation. It looks like a P. Let me go find it. It's not a P though. I know it's hard to keep the Greek letters from the regular letters straight. I'll find it. There it is, right here. Doesn't it look like P? It's rho. Yep. All right. Plots. In all of the examples that I'm giving you extra stuff that you don't necessarily need in any assignment just because I want you to have an example of how you'd get this. Pictures are always going to be something extra. In this case, I'm asking for a plot that has a matrix of scatter plots and histograms combined. It's super cool. So I'll show you what that looks like. Var, do you know what that does?
Identifies the variable.
It identifies the variables, not variance. So these words right here, these are variables in the data set that goes with example 2. They are the names of the columns. That means when you take this same code and you want to manipulate it to be able to do your homework, you would have to change the names of the columns to refer to the columns in your homework data. For example, there are 2 quantitative variables in your second homework, number of fits thrown and number of pleases heard. Your homework is set in a preschool. I write about what I know. The preschool has 2 classrooms. There is Miss Molly and Miss Beth. My son is in Miss Beth's room. Some of his best friends are in Miss Molly's room.
Oh, no.
Yes. Well, fortunately, they all get to play together on the playground and during after school. So they handle the separation well. But yes, so when you're doing your homework, these are the names that you have to change to go with your columns. Likewise, you have to point it towards your homework database. Stata code. Let me see, where did stata code go? Yeah, I've got, where did it go? I lost it. SAS syntax. Okay, it's coming later. So we'll do the SAS output first because the output looks very much the same in both programs. So here we go. This matrix right here has 4 rows and 4 columns. It's square, meaning it has 4 rows, the same number of rows as columns, but it's symmetric. So half of it is redundant. So for instance, if I'm looking at this set of numbers right here, this provides information about the association between family income in thousands and family income z-score. So the relationship between family income thousands and family income z is exactly the same as the relationship between family income 1,000 and family income z. So this number and this number are telling you the same thing. Likewise, this number and this number are telling you the same thing. So in practice, you can look at the diagonal of this thing and either below it or above it. And when people report correlations in text, in manuscripts, they don't report the whole table because half of it's unnecessary. So what are these numbers? Well, the first number is covariance. So let's say if we want to look down here, this is the association in terms of covariance between family income z-scored and years of education. So they are related as 1.37 $1,000 years. What do you think about that? Yeah. We gotta fix it, right? $1,000 years is not a thing. 1.37 $1,000 years. No idea what the hell that means. The only thing I know is that that number is positive. So what is a positive association between family income and education? Yeah, this way. Yeah. More money, more school. Isn't that all why you guys are here, right?
More money.
Yeah, sorry, it hits too close to home, huh? So that's covariance. This number right here is the variance of the variable in the row, so that's the variance of education. The next number down is the variance of the variable in the column. So that's family income z-score, which has a variance of 1 by design. And then degrees of freedom. That's based on your sample size. So note in this table, the degrees of freedom are given for every combination because it uses whatever information you have. So there are 99 cases that have education. Excuse me, there's 100 cases that have education, looks like. There are 101. It's n minus 2. But there's not as many people who told you how much money they make. So these numbers can change as a reflection of missing data. How many complete pairs do you have? Now that table, as I said, is for pedagogy. There's nothing in this table that will help you actually answer the question of whether these things are related. The next table, this is page 8. This is where the information that is useful hangs out. Okay. So I have 3 different versions of family income here to try and make a point. Would you do this in life? No. This is for pedagogy. I have family income in thousands, family income z-scores, and family income that's been log transformed. Note that family income in thousands and family income z-score have a correlation of 1. Does that surprise you? It's a z-score transformation, which changes the mean of family income to be 0 and the standard deviation to be 1. It is a linear transformation. It changes the values evenly. And so it is the same variable on a different scale. That's why it's perfectly correlated with itself. That is not the case between family income z-score and the natural log of family income. It's a nonlinear transformation. It's not the same information anymore. And in this case, it squishes together the rich people and it spreads out the poor people in terms of what it does to the distribution. The next one is education. So our previous covariance told us about the relationship between income and education in terms of dollar years, $1,000 years. This is after standardizing these variables. So after correcting for the differences in mean and standard deviation, the Pearson's correlation between family income z-score and education is 0.45. So we know it's positive from before. It's still positive. What's the most it could be? What's the highest a correlation can be? 1. So It's not 1, but it's not 0. It's right in the middle. Now, do you think this is different than 0? Is 0.45 enough of a difference between 0 that you'd call it, oh, it's pretty unlikely that if it were 0, we'd get this result? We need a test. So if you want to do the test, you have 2 options. One of them is going to be preferred. You take that correlation of 0.45 and your sample size of 97 people and you plug it into this formula. That's option 1. Or you read the line below it, option 2.
Ooh, let's go with 2.
Go with 2?
I'll take 2.
Take 2? Correct. SAS is better at it than you, I promise. It's much better at it than me as well. So let's decompose what this value is. This is our p-value. It's the probability of observing a correlation of 0.45 if the true correlation were 0, given that we have 96 observations that this is based on. That's the Proc-Lisa interpretation, by the way. SAS is not that nice to you. Here's what it calls it. Let's unpack that. That value right here is the prob greater than bar R bar under HO rho equals 0. What the hell is that? Okay, prob is probability. So it's the probability of observing an R. Do you know recognize what the bar does? Absolute value, right? So it's agnostic as to whether we're talking about a correlation of 0.45 or negative 0.45. Doesn't matter. They're the same size in terms of magnitude. It's just a different pattern of relationship. Under HO, what's that?
Null hypothesis.
Null hypothesis, meaning what do we expect? That rho equals 0. The population correlation equals 0. So, yeah, that they don't do the p-looking letter. They just print out rho. So less than 0.01% of the time, we would see an R this big with 96 people if the true R were 0.
So it is.
Yeah, so we would say, yes, it's significantly positive. We reject the null hypothesis that it's 0. It is sufficiently unexpected that we're calling it noteworthy. All right. With me so far?
So because we're looking at the next line, which is highest year of school completed, and it's so small, we're happy with that?
We're happy with that. So this, these 2 things right here, education is the name of the column.
Right.
The label that goes with that column name is highest year of school completed. So that's one thing. This is where it's advantageous to have labels because you can make your output more readable to remind yourself what the variable names are. But now your question, I think, is how did we decide to call that significant? Is that
Or how did we get that number?
How did we get that number?
Because you first said, well, here's the formula, and then you said, well, SAS completed it. So that's what SAS went ahead and completed for me.
What is not shown here is the intermediate step of the t-value that generated this p-value.
And so you told us how to get there, but you're just kind of saying, like, here's what ended up coming up.
Yeah, so this is the step it hid from you to make the t. Once it has the t, you figure out where you are on the distribution.
Oh, right, and then we go back to the fancy table.
And then the table is built in to SAS. And so it generates a t, and then it gives you the exact area that would be beyond that t either on the left or the right. So this is two-tailed, meaning that we would accept a positive correlation as unexpected or a negative one. So it's the area that corresponds with the result that extreme. Bigger in terms of more negative than negative 0.45, or bigger in terms of more positive than 0.45.
So 0.0001 is right in the
Right in the middle is the t of 0. P is the amount of space in here. So all these distributions say integrate. The total area under this curve is 1. What we're trying to figure out is what is the point at which we would say that we're at the confidence level that we select a priori. So if we want 95% confidence, that's alpha equals 0.05, meaning that 5% using both sides would be where unexpected is, where we say that this is enough information to say it's not likely. And where we are is less than 0.05. We're way, way out here. And so it's giving you the p-value, the area that corresponds to that exact location of the t that comes from your r. So the t value is inconsequential. Its only use is to figure out where the probability is of finding a t that big. The probability is what we're after. Not making it better, am I?
No, I mean, I'll get there.
Do you want to see the t? Would that help?
Well,
Because I can make you one.
We're talking about p or we're talking about t?
So we're talking about 3 different letters here. Actually 4 if you count sample size. Yeah. See, didn't I warn you on day 1 that this is about working memory and language, having to keep all this shit straight? Especially when they reuse letters, which is not cool. But they do it anyway. So what we have in terms of our letters here, our collection O letters, we have R. That's our index of association. That's what's going to be known more generally as an effect size. How strongly related are these 2 variables? We have an answer for that. Next question is, how believable is that R? Is it like my correlation is 0.45 or 0.45-ish? And our intent of believability is a function of sample size. That's n. So we put those 2 pieces of information together to try and locate this R on a distribution that tells us how expected R would be. The result of putting R and essentially weighting it by sample size, downgrading it if it's a small sample, upgrading it in terms of the precision, gives us our T. So T is a location on the T distribution. This thing.
Yes, I think I'm with you up to there. So, what is the negative point?
Okay, let me go to this picture right here because I like this one better because it has the critical values on it. Let me see if I can zoom in so that you can see the tiny little print at the bottom.
Are we testing for 90% significance?
Well, we have what we're supposed to do. We are there.
Okay.
We are there. We are supposed to decide a priori, without looking at the results, like where we're willing to say significance starts.
Right.
The most traditional definition is an alpha of 0.05. So we're looking for a probability, a p-value, less than 0.05. That's where the demarcation is. So this is z instead, but it will be, for a sample size this big, it'll be exactly the same shape. If we had a z of 1.65, let's say that our t came back with that, then 10% of the time, this way, we would see a t that extreme would only happen 10% of the time this way, or 10% of the time that way. This way, let me see, I think, okay, hang on. They've divided it for us. So do you see this up here that says significance level p-value?
So the point -0, or the smaller than 0.0001, that's the p-value?
Yes,
Okay.
that's what it is. And so, like, here's where the p-values start. Like, this is the 10% mark, the 5% mark, the 1% mark. We're way out here.
Okay. I think I was confused with the labeling.
Yeah, it's actually giving it to you as a less than sign, not as a negative sign. Because p-values are never 0. They're always less than some tiny number at the smallest they can be.
Yes.
So putting that together, the decision is, we say, yeah, we have enough evidence based on our original standard of accepting only 5% things to be unexpected by chance, that this number, this R, this effect size is not 0. We reject the null. It is statistically significant. It is sufficiently unexpected that it's noteworthy to us.
We reject the null because it's not in the key.
We reject the null because that p-value is less than 0.05. It has exceeded our threshold for where unexpected begins.
Oh.
That threshold is set by our alpha in advance. It's roughly a t of plus or minus 2 for a 95% confidence interval / 5% alpha. Here's some more stuff. How precise are these correlations? In the same way that we can't interpret what a mean is without knowing its standard error, we can't interpret a correlation without knowing its standard error. The trick, though, is that we can't compute it directly because correlations are bounded and the standard error can make it go outside the boundaries. So this is where our friend Fisher Z comes in. And so that's what this next table is giving to us, is the results from the Fisher Z transformation that unbounds the correlation so that we can get standard errors and confidence intervals for it. So for instance, a correlation of 0.80 between family income z-score and family income log corresponds to a Fisher Z of 1. This bias adjustment thing is the difference if you want to adjust for sample size. That's the thing I said before that exists, but I've never actually been asked to do it. So here is the correlation estimate after you adjust for sample size, and here's the confidence interval around it. That confidence interval does not include 0.
And we're comparing the Fisher Z to our confidence.
The Fisher Z is just a means to an end to get this interval.
To get that interval. And then
That's what it's for.
And then we would compare that to our correlation.
That's right.
Got it, okay.
So this interval tells us, if we redid this study over and over and over again, this is the interval that the population parameter, in this case correlation, would be in. So the fact that 0 is not in here means that our result is significant. It is unexpected. The size of this interval depends on your sample size. More people, smaller interval. Here's another example of a different kind of hypothesis test. Let's look at the correlation between education and family income z-score, this line right here. So up above, we saw that the p-value that corresponds to a correlation of 0.45 being different than a null hypothesis of 0 is less than 0.0001. 0.45 is significantly bigger than 0. The confidence interval around 0.45 is right here. It ranges from 0.27 to 0.59. This extra piece right here that I requested is a different null hypothesis test, changing the null. What if the thing that I expected was 0.5? Same idea. What if research says that education and family income should be correlated 0.5 in the population, and in your sample you got 0.45? Is that close enough? Or is your sample somehow different / suspicious? Same principle as the Subway sandwiches, right? 11 inches instead of 12, is that suspicious? If you expect 0.5 and you got 0.45, is that close enough?
No, because it's not in the middle. Is that what you're saying?
Well, 0.5 as a guess. Another expectation is an arbitrary number I picked for this example. You could pick whatever it is, but I'm saying, like, let's pretend that I have all of this previous research in which the research suggests that these two variables are correlated 0.5. And I collected those same two variables, but I got 0.45 instead. Is that close enough?
Is that where you look at the p-value at the next column?
Yeah, this next column is doing the same idea of testing a correlation against an expected correlation. But rather than testing it against an expected correlation of 0, it's testing it against an expected correlation of 0.5.
So they're pretty close.
So 0.5 is within this interval, for sure.
Right.
So yeah, it's 0.45 is well within expected territory relative to 0.5. It would happen with a frequency of like 53%. You'd get a correlation that far off. So this would be, we retain the null, we do not reject, meaning this is non-significant, meaning that it is not different than a correlation of 0.45. So it is most common to test associations against 0, but you don't have to. You can test them against anything you want. Here's a picture. Isn't this pretty? I like pictures. So on the diagonal, going down the middle here, those are histograms. On the off diagonals, those are scatter plots.
Just repeating it.
Yep, these are scatter plots. And so family income z-score and family income in thousands are linear transformations of each other. That's why their correlation is perfect. Whereas if you look at this one right here, this is the example of what a log transformation does. On the log scale, it reels in. So the difference between like where you are here and where you are here on the x-axis is a lot smaller than the difference on the y-axis. So this is a non-linear association between these variables. And then you can see here's a scatter plot of education versus income. So I have this square highlighted because I'm going to show you a more specific version that has a line through it that shows the slope. But if I told you to make your best guess just eyeballing this as to what the correlation would be, would you have any clue? I wouldn't. I'd be like, it looks messy. It looks zero-ish to me, but it works out. This is what it actually is. This is where the correlation of 0.45 is shown visually. Now, where we get the slope of that line is coming later, because the slope of the line is only the correlation if you're talking about the z-scored version of the variables. But here is the best fit line through these points, assuming that the line should be a straight line, linear relationship. And I did that with something called proc-gplot, sgplot, to make pictures. Okay. So words. How would I talk about what I just told you? First step, describe your variables. If you haven't already done that in a method section, such as the one that you completed for your first homework, it would be good to do this in here. So we're examining Pearson's correlations to see the extent of a linear relationship between years of education and family income. We selected a two-tailed alpha of 0.05. That means a priori we are declaring our line in the sand as we only want unexpected to be 5% of the time. So in terms of writing the results, the formula that I mentioned last time holds here. It's always stat, 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 comma, words. Years of education was significantly positively related to family income in thousands. R equals the strength of the association, the p-value that comes from locating that association on a t-distribution with that degrees of freedom. R adjusted is the version of R after correcting for sample size, just in case reviewer 3 needs it. And here's your 95% confidence interval for the R that describes the level of precision that that estimate affords us given our sample size. Then the all-important comma, indicating that. I like indicating that. Such that is another one. You can mix it up what comes after the comma, but the important part is to put the interpretation there. Such that greater education was associated with greater family income. Greater with greater, greater with lower. That's how you put the idea of a positive versus a negative correlation in words. Note the use of non-causal language associated with. I didn't say having more education results in you having more money. Or having more money results in you having more education. How cool if those would both be true, because we measured these things together in an observational study. So I'm not claiming one caused the other or preceded the other, just that they're associated. And so then my extra piece for you guys, our sample R of 0.45 would be expected less than 0.01% of the time if the population correlation were 0. And then the hedging of my results, just in case this guy, right? I've got one fairly aberrant data point. So to hedge my bets that that guy isn't throwing off all of the relationships, I'm looking at the same extent of relationship with log transformed income, in which he is reeled in relative to the others, and the results are very much the same. So you can think of that as a robustness test to the association of your variables. Robustness, yes. Robustness basically means how similar would it be if I messed with it a little bit? And if you mess with it a little bit and it stays the same, that's good. It's robust. Stata folks, I didn't want to leave you out. Here are 2 lines. Now, I did not know this until the first time I tried to do this in Stata, so I want to make sure that you know this, just in case you have missing data in your lives, which is very common in real data. The first option, correlation. I'm doing the same thing that I did with ProcCore and SAS, listing the names of the columns that I want the correlations for. In Stata, options are separated with a comma. So the option after here is that I'm asking for a covariance. So it's spitting out this little covariance matrix right here. So this is the idea of $1,000 years, the thing that's not helpful. What I didn't realize is that Stata does something called listwise deletion when it computes this, meaning that it only uses the cases that have all the variables you listed. Anybody with partial information is removed. That is different than what SAS does. So that is why I had to ask for a second line that in theory is redundant, but actually isn't because of missing data. PWCore stands for pairwise correlations. I'm again listing the names of the columns for which I want all pairwise correlations. SIG means give me the p-values. That's not something that they do by default. And OBS means list how many people contributed to each correlation. So then you get the Stata version of that correlation matrix, which is very much the same. The only difference is that whereas SAS that says less than 0.0001 for its p-value, Stata gives 0 to however many decimal places it reports. So the p-value is not actually 0, it's 0 to 4 decimal places. And then it gives the sample size underneath. To get the Fisher-Z transformation and the confidence intervals, I had to track down a user-written package. So one of the things that's nice about Stata, and the same is true for R, if people want to program in something that Stata doesn't have, they can do that. And there's a network by which you can search for these things and download them to install into Stata. And I have checked, and that is possible to do inside the University Virtual Desktop. You can download these things and install them. You don't need administrator privileges. And of course, you can do it if you have your desktop version. So I asked the Google, how do I do a Fisher-Z transformation in Stata? And this is what came up. It's a package called CI2. And so I'm telling it to install that package. and then I'm using that package for these two variables, and this is the output that the package gives me, and it matches that of SAS. The only difference is that it's using the non-adjusted correlation, the one that is not adjusted for sample size. And then here's how you would make the pictures in Stata as well. All right, questions? Funny?
No, I was just thinking it'll make more sense once I put it in practice.
Once you put it in the process? Yes. Me standing up here and talking about fake data is not how you guys are going to learn this stuff. It is not. It is how you get started. But being able to run these techniques on data you care about, to answer questions you care about, that's how you learn this stuff. I can give you opportunities to practice, but that extra piece is really the thing that's going to make a difference. And that's true not only in IntroStat, but as high as you go. Doing it on data you care about is the way to make this stuff actually stick. Let's see, where are we at? Oh, 15 whole minutes left. Hooray for me. I know. So I thought I was out of time already. I just have so much fun up here that I forget where I am. Okay. All right. So Pearson's R, we pick up on slide 32, is not the only game in town. The word correlation has lots and lots of adjectives that go in front of it that denote sometimes different kinds and sometimes the same kind that goes by a different name. So here are some synonyms that I want you to be aware of. If you have two binary variables, meaning 2, 0, 1 variables, you can compute a Pearson's correlation between them, even though they're not technically quantitative. A positive correlation would mean that being a 1 on X is associated with being more likely to be a 1 on Y. A negative correlation between two binary variables would mean that being a 1 on X is associated with more likely to be a 0 on Y. But it's perfectly fine to do that. That correlation works out, has a computational shortcut if your variables are binary, and the name of that computational shortcut goes by the name of a phi correlation. It's still Pearson. So you will see it reported as a phi correlation. It is the same thing. Likewise, if you have a quantitative variable and a binary variable, there's a computational shortcut that goes with that, and that is called point biserial. It is the same thing. These are synonyms for Pearson's correlation. Here is one that is not the same. Another old white guy, Spearman. A different type of correlation is a better choice if you're in one of two situations. One is that you are afraid that extreme values of your quantitative variables are going to bias your results. Extreme values are known as outliers. So if you're concerned about that, Spearman's is what you might do. The other is if you have ordinal data. Remember ordinal? Like if I have a scale where my choices are strongly disagree, neutral, agree, that one, I can label those responses 1, 2, 3, 4, 5, but they're not really numbers, right? We can agree on the order, but the absolute value of the numbers is not something that we can establish. So in either of those cases, you're suspicious of extreme values or you have ordinal data, Spearman's correlation is what you can ask for instead. And just to mess with you, they call Spearman's correlation rho instead of R. Even though rho is population correlation. I'm sorry. I know. I don't know why they do this to you. I'm trying to be consistent with how the world uses these things. In practice, I would never just give the letter R or the letter rho and expect people to know what the hell I'm talking about. I always put the words with it. Spearman's correlation or Pearson's correlation. The way that this works is through data transformation. You, meaning you tell the software to do this, it sorts your variables by value order. it then gives the rank. So the highest value gets a 1, the next highest gets a 2, the next highest gets a 3, and so forth. It sounded familiar?
Because they did that by hand.
Because you did that by hand. I'm so sorry. Yeah, no, software will do that for you. It sorts it by rank. It then runs Pearson's correlation on those ranks.
Awesome.
And everything else is exactly the same. Once you have your correlation value, you feed it into the t-test machine using your sample size. Out pops a p-value, and that gives you your probability of observing a correlation that big if the null hypothesis were true. So here's some examples of when you would get different answers for the strength of your association between Spearman and Pearson. So first plot over here, x and y. This plot generates a Pearson correlation of 0.37 and a Spearman correlation of 0.35. Basically, there's no difference here. This plot right here, a Pearson correlation of 0.88 for the plot in the middle. Now, does that look surprising to you that it would be that low? Yeah, it's like all snaky, right? Pearson's correlation is linear. You try to draw a line through this thing, you're going to miss some of the plots. Even though if you stare at it, it's like, no, that's a really strong relationship. Spearman's correlation would be perfect. Because if you don't adjust for the relative distances between these, if you just stack them up next to each other, then it is a perfect correlation. An example of when you would have outliers that you would be worried about, here's one for this. So these cases over here on x are super far away if you use the original value of x, and so that's why the Pearson correlation is only 0.67, because it's trying to draw a line through all of this stuff simultaneously, and these guys over here are sort of ruining the line. They are. Get in line, come on. But if you took away the distance between these things on x, if it was just the rank, like this guy's next, then they're back over in line, and the Spearman correlation is 0.84. So in practice, I would say these are used more for ordinal variables, but it can also be another version of a robustness test. If you have some people out here that you're concerned about ruining your line, reporting both forms of the correlation is a good way to hedge your bet. And do you know how you do that? One word. Let's play Where's Waldo? Here's another example of proc core. What's different this time? The word Spearman. Guess what that gives you?
Oh, a Spearman.
Spearman correlation. And I asked for Pearson too, so you can get both of them at the same time. So yeah, it's just knowing how to ask. In Stata, there is an option called Spearman that you invoke to get those correlations as well. Yeah. So when would you do this? Well, here's an example where we have family income. That's in the log scale. We're just taking that one. We have a 7-point response variable about how often you socialize with your friends. And here's another 7-point response scale about how happy you are. Let's look at that one. So it's supposed to be 7 points. Did everybody use all the categories? Nope, the lowest is 3. No one wants to admit that they hate life. Not on a public survey.
Also, not everyone responded to that question.
Also true. Yeah, only 73 people. We don't know what happened to the other people, but it's possible they didn't want to answer because they hate life. Possible they didn't get the question because they got a different version of the survey. We'd have to know more about where that came from.
And missed the bubble.
Missed the bubble, yep. That could happen too. But if we look at the mean and the median for this variable, the median is 6. The mean is 5.5-ish. What does that tell you about its distribution without even making a picture? Yeah, gestures, right? Where is the mass? Is it on the right side or the left side? Right side. The middle value, the 50th percentile, is 6, and it only goes up to 7. So there's a whole lot of people who answered 7 and 6, and not very many people who answered all the way down to 3. These last two are ordinal variables. Even though it's really tempting to look at these numbers and treat them as numbers, they correspond to verbal labels. They're not numbers. They're not. So we can do a correlation on those that acknowledges that, and that's Spearman. Family income is quantitative. That one we don't have to worry about as much, but if we want to do cross pairings of correlations, then we need the Spearman. So if we pretended all of those numbers were numbers, here are the Pearson correlations. If we acknowledge that the latter two sets are not numbers but are actually ordinal categories, then Spearman is the one that we would look at. How about this one right here? Can you see that number? Make it big. Yeah, correlation between log income and how often you socialize with your friends. Spearman correlation, so it is the correlation between the rank order of log income and the 1 to 7 scale of socializing with friends. That is a negative correlation, 0.3. Is that a huge relationship, sort of medium, or no relationship? So this is an R. What's the metric of R? What's the biggest it could be?
1 or -1.
1 or -1. What's the lowest it could be, I guess, the smallest relationship? It'd be 0. So this is minus 0.3. So what does this tell you about the association between how often you spend time with your friends, where higher scores mean more often, and money, where higher scores mean more money? It's negative. So people who spend more time with their friends make less money. Or people who make more money don't have time for friends. Whichever, right? Now, is that significant? Here's our p-value. The probability of observing a correlation of minus 0.3, if the true correlation were 0, that would happen 0.9% of the time, less than 1%. So what do you think? Is this significantly different than 0?
Yes.
Less than 1%? Yeah, our cutoff is 5%. So yeah, we have strong evidence to suggest that this is unexpected. This is different than 0. Reject the null. How about this one? Does money buy happiness? Sometimes, up to a point, right? That's what the research shows. There's some magical point where if you're struggling, then having more money makes you more happy. But if you're okay, then maybe having more than that doesn't help you. But what do our data suggest? Correlation of 0.12.
And that's really close to the 0.
It's pretty close to 0. Yeah, it's just slightly positive. So it looks like money and happiness, more money, more happiness, a tiny bit. But what do we think about that? How often would we see a correlation 0.11 if the true correlation were 0 in a sample of this size? Like 35% of the time. This is well within expected territory. So this is a case of non-significant correlation. It is not significantly different than 0. We either do not reject or retain the null, whichever way you want to talk about it, but people don't say that in the real world, which is why I'm out of practice saying it. This would just simply be called a non-significant correlation. If you want to be completely transparent in your reporting, I would say it is non-significantly positive, because direction does matter. But we don't have evidence to say it's different than 0, not with this sample size. And how about spending time with friends and being happy? Surprisingly, yeah, about the same. Slightly positive. But in interpreting that result, one thing to keep in mind, this distribution right here. Everybody's happy. Everybody lies, quite possibly, but from the perspective of prediction, if there's not a lot of variability, it's hard to predict a variable like that. You can't predict a constant. If everybody says they're happy, then there's no room to show an association with other things. That's what's known as range restriction. Yeah. So that would be a caveat, a section for your potential limitations of this study. However, everyone lied and said they were happy, and therefore that reduced my capacity to show prediction of this variable, relations with other things. Yes, well, lying and self-report, that's a whole nother thing, but that's not this class. That's another class. Whether or not you should trust people to answer questions, that's not my business. My business is once the data come in, right? All right, and so here's the example results section that goes with it. I just switched, literally it's like a find and replace, Spearman's row, and then describing each of those. Rather than doing R, I wrote out row, because that way it's Spearman's row rank order correlation, doing those things. Okay, and there's the Stata code, like I said. There is, a special thing I had to download to get medians and Spearman's stats, and it asks for row, observations, and P.
So do we have to download it?
You don't, Spearman's already built in. It's to get the median for these variables. I found this little thing, but you don't need to do that. Technically, I think you can do, what's it called? Summarize with the detail option. That gave you medians for your first homework. This just does it in a little bit shorter output. So Univar, that little package that I download, gives you it in this nice little friendly format, rather than having a whole shit ton of output you have to scroll through. Yeah, what's the sign for shit ton? I'm curious. Okay. I'm learning all sorts of new things. She spelled it out, okay. I would be impressed if that were a symbol that were anticipated. That's part of my Midwestern vocabulary, shit ton. All right. Okay. So we're almost through this. The next thing is how to get the same types of associations among categorical variables. And that will be our new friend, chi-square, C-H-I, the Greek letter.
Chai latte.
Almost. I think that has an A in it. I didn't do it. Yeah, that's my battery dying. Okay.
Right in time.
Yep. All right.
Perfect timing.
That's perfect timing. All right. Well, let me know if you guys need anything. Otherwise, have a good weekend because it's Thursday.